Hello, today we're going to discuss the fact that the hypotenuse of reduced Pythagorean triplets that hypotenuse would be the sum of two square integers. Okay, and we're going to discuss that. This assumes some degree of knowledge. I've been out of the game for a while, so I really appreciate those of you who've been regular subscribers who've held on. This might be, we're going to do the best we can in getting back in the game here. I want to say thanks to all my regular subscribers and especially those who've helped out with math and science. A special thanks to Math for Physics, who's helped out a great deal. Let's go ahead and get into it. We're considering reduced Pythagorean triplets, and this is our form for reduced Pythagorean triplets. Okay, let's say 3, 4, 5, 8, 15, 17, 9, 40, 41, so forth. Okay, and in our form for reduced Pythagorean triplets, we are considering the we're going to be proving that the hypotenuse is the sum of two squares. Okay, that x and y are in fact integers. Okay, now you can see clearly that if you square this and you add the square of that, you get the square of this. Okay, no, you can't, because you can't see clearly at all. There you go. The square of x squared minus y squared plus the square of 2xy gets you the square of x squared plus y squared. Okay, but you can't, it isn't readily apparent. Now that you can prove algebraically, but it isn't readily apparent that they must be integers. Okay, so let's go along. We have we know that x squared plus y squared is an integer. We know that 2xy is an integer, and we know that x squared minus y squared is an integer. That we know. Okay, now let's go into why we know that x squared plus y squared is an odd integer, that x squared minus y squared is an odd integer, and that 2xy is an even integer. Okay, so let's consider through a process of elimination. Let's say all three sides were odd. The square of an odd plus the square of an odd would then have to be the square of an odd, and that's illogical. Let's say that we have an even side and then an even hypotenuse. Well, that wouldn't be reduced, okay, because it would be a factor of, in order for a Pythagorean triplet to be reduced, then there have to be no prime factors in common. Okay, so by so we can't have all three sides. Let's say we had odd, odd, even. Okay, well, if we have an odd, odd, even, then we have the even squared would be mod 4. Okay, and each of the odds squared would be 1 mod 4. We'll add 1 mod 4 and 1 mod 4, you get 2 mod 4, and that would not be mod 4. Okay, so either this or this must be even. But if this is odd, then let's consider the idea that this would be even here. Okay, if this is odd. If this is odd, then let's get that really close. If this is odd, then we have x squared plus y squared is equal to an odd number. Okay, now one x squared or y squared in that case must be, either one of those must be even, right? Okay, and the other must be odd. You can see that just kind of heuristically. You don't need to have that proven. Let's take the case of x squared is even and y squared is odd. We'll look down below. That's an even minus an odd. That's going to be an odd, not an even. And the other way around, an odd minus an even. We're considering x is greater than y, by the way. Okay, an odd minus an even would be an odd. So for this hypotenuse to be odd, then the base would have to be odd too. So 2xy is going to be our even, and that's going to mean that if we skip down here, since 2xy's are even integer, then xy is an integer. Okay, whether it's odd or even. Let's get that. I think I have time. Let's try to hustle. Okay, and x squared plus y squared is equal to an odd integer, and then x squared minus y squared is equal to an odd integer. Now, everything that I've done so far, you can verify in other sources. There are all kinds of windows over there to the right with all the professionals and all the, with professor suits on. Me, I'm kind of, I have my own unique style, and a lot of you appreciate it. But okay, so x squared plus y squared plus x squared minus y squared is equal to 2x squared. An odd integer plus an odd integer is an even integer, thus x squared equals an integer. Now you can do the same process through subtraction and arrive at that y squared as an integer also. Okay, so x times y is equal to an integer, and then x squared and y squared are integers. Now if x squared and y squared are integers, then x is the square root of an integer, meaning integer 1 would be the same thing as x squared. Okay, and then y is the square root of integer 2, which is again the same thing as y squared. And then we have a case such that the square root of integer 1 times the square root of integer 2 gets us, I call it integer 3, but that's really xy, okay? And that's right over here. Now let's consider different cases. If x squared minus y squared is equal to 0, in other words, if y equals x, then no Pythagorean triplet, no problem. We're not gonna worry about it too much, okay? Because that's just not a case we're going to consider. Because that just means a side of 0, and it means no triangle, and I'm not going to waste my time with that. Then two possible cases. If x is greater than y, and x must be greater than y for this to be a scalar, okay? Then two possible cases. Integer 1 and integer 2 share prime factors, because again, you need to multiply these together such that you have the square root of, this is actually the square root of some kind of a square integer, right? Because by definition, you need to match these such that you have the square root of integer 1 times, if I were to just take a big long radical and extend it over integer 1 times integer 2, I would need to have matching prime factors to have the square root be an integer, okay? And not some kind of other type of number, okay? So integer 1 times integer 2 together would have to have matching sets of prime factors in order for the square root of integer 1 times integer 2 to be an integer. Now, if they share prime factors, then the problem is we don't have a reduced form here. Because then x squared, integer 1 and integer 2 are the same thing as x squared and y squared. And if these share prime factors, and look, we don't have reduced form. This shares prime, x squared and y squared share prime factors, and then x squared and y squared here share prime factors. Guess what? We don't have reduced form, okay? So that's not going to work, is it? And in fact, right here we have x times y, and then we have x squared minus y squared. We don't have reduced Pythagorean triplet form. So that's not going to work. Now, what will work? Okay, second case. Integer 1 and integer 2 both have, what did I write there? Double sets of prime factors. Okay, in other words, this has matching prime factors. Let's say it's 3, 3, 5, 5. And this has matching prime factors. Let's say it's 7, 7, 11, 11. But guess what? If these have double sets of prime factors, then in fact, they are square roots of squares. Because 3 times 3 times 7 times 7 is a square number. Okay. 2 times 2 times 3 times 3, that's a square number. So the square root of a square number is an integer. Okay, then there are the squares of integers. Hence, x squared and y squared are square integers. But if so, then x and y are both integers. Okay, now remember that x squared plus y squared is equal to the hypotenuse of a reduced Pythagorean triplet. Thus, a reduced Pythagorean hypotenuse can be represented as the sum of square integers. Okay, now I haven't touched on questions of uniqueness or anything like that. That I might have to review a little bit. The question of a unique case, whether it can only be the sum of square integers. I believe it is the case, if I recall, that the integers for a given reduced Pythagorean triplet, that it must be the sum of a unique set of square integers, but I have to review that a little bit more. So if any of you want to make a video proving that, I'd greatly appreciate it. Thank you.